Now, getting a little more specific, in the Atwood machine problem, the first thing we want to understand is that counterclockwise motion is positive. Okay? Now that's the convention. If you want clockwise motion to be positive, you can use it, but you've got to say explicitly, okay, I'm going against convention here, I'm going to let clockwise motion be positive. Better off just to consider yourself on the other side of the machine where the clockwise motion that you want to analyze is now counterclockwise. Okay, and you can kind of work out that. Still, you do have a choice, but this is the default, so if you don't say anything, this is assumed. Okay, now, if you had no mass on one side, then this thing would be in free fall, wouldn't it? Okay, by free fall we mean falling under the acceleration, under the influence of gravity. So you're falling at the acceleration of gravity, because there's nothing on the other side to hold you back. Okay, so the acceleration then is the acceleration of gravity. Remember, we measured the acceleration of gravity in class and got something like 12.5 meters per second squared. Okay, now that was just by dropping something and doing a kind of a 1, 2, 3, 4 count, I think, and figuring out that it looked like it dropped a meter in 4/10 of a second. And I think that's what comes out 12.5 meters per second squared. If we refine that, as we could easily do now with the vernier interface on a microphone or in any other of a number of ways of determining it, we get something much closer to 10 meters per second squared. And the accepted value, if you don't know where you are on the surface of the Earth or off the surface of the Earth, if you're close to the surface of the Earth, you kind of assume 9.8 meters per second squared. But that varies from location to location, even with the same altitude. The Earth bulges at the equator, density of the mass beneath the surface varies from one place to another. So I don't think there's any place where it's actually 10 meters per second squared, but it can go 9.81, 9.82 meters per second squared. And if you change your altitude significantly, it changes more than that, as we'll see when we talk about Newton's law of universal gravitation. Okay, so if then with the Atwood apparatus, we observe that every mass transfer, that would be every paperclip transfer, every transfer of some equal amount of mass from this side to this side increases the acceleration by 20 centimeters per second squared, then what do we conclude about the percent of mass that's transferred each time? Well, you know, we had to do a little thinking. As one person came up with it. I'll just say 20 centimeters per second squared is 2% of 10 meters per second squared, isn't it? So, or if you divide this into 10 meters per second squared, you get 50, which means that you would transfer 50 masses before you got to an acceleration of 10 meters per second squared. So each transfer is 1/50th of the total mass. Okay? And actually, you wouldn't have transferred the whole mass. You'd have transferred the mass on one side to the other. But the other thing is, each transfer changes the net force, would change the net force by 2%, meaning that the amount of mass you're actually transferring is just 1%, because remember, if you transfer 1% of the mass from here to here, that increases the force on this side by 1% of the total weight, and decreases the force on this side by 1% of the total weight, so that you have a 2% change in the net force. So we put all this together, and we figured that the amount being transferred has to be 1% of the total mass, if that's the slope of your acceleration versus n, your number of clips transferred graph. Okay. So this shows you how to figure out the mass of a paper clip if you know the total mass of the system. And the masses were, 100 grams, 200 grams, and 400 grams for the various systems. Okay, so we talked about how to interpret a graph of the acceleration versus the number of cliffs that have been transferred. Okay, what's the slope of this graph mean? Okay, slope of the straight line mean represents what? Now, this would be the type of graph we would get if we had data points from our calculations of the acceleration and fit the best straight line to those data points. Now, this isn't a very good fit. This line is a little too steep, should be shallow. But these points, just kind of put those points down on the board. So there's no real accuracy in what I did here. So this is a representative diagram. In any case, you put your points down, you figure out the straight line that you think fits best, and then you calculate the slope of that straight line. Well, that's fairly easy to do. But what's the meaning of that slope? Okay, well, to determine the meaning of the slope of a graph, the slope is rise divided by run. So what's the meaning of the rise and what's the meaning of the run? Well, the rise represents the change in whatever quantity you're measuring here. That's the acceleration. So the rise is a change in acceleration, and the run represents the change in the number of clips. So that the slope represents a change in acceleration over the change in the number of clips that have been transferred. And that's the additional acceleration you get per clip. So from your data, you could figure out the number analogous is 20 centimeter per second squared, and you could then reason out from the known mass of the known mass you had suspended, you could figure out the approximate mass of a clip. Now there's one caveat there, and that is it's a little more complicated than that. Okay, first place, the clips that you had really kind of added a significant amount of mass to the system. So if you had 250-gram weights and 14 clips, those 14 clips might have a mass that's 4 or 5% of the total mass. So this 1% of the mass should be total mass, which would be the weights, the mass of the weights plus the clips, not just the mass of those hanging weights. That introduces a little bit of algebra into the calculation, and that's something I kind of expect you to try to deal with. Okay, so there's one little caveat there. I didn't mention that in class because I wanted to get through some of the main ideas, and I think we got through at least the idea of work and energy. Okay, so now I want to talk about this diagram, but I'll talk about it in a separate video.